All right, so let's see. Today we'll finish up full analog review, at least give you guys a chance to ask me questions. We'll talk a little bit about DMA, and then I'll go over student presentations and give you some examples of what good student presentation is and maybe some pitfalls that students have had. Any logistics questions to get started?
No, everyone's.
You should be excited. This is the last class where I'm going to have to teach you anything. I'm taking a break after this. You guys are going to teach me things. Other guest speakers teach you things, but I don't have to teach. You don't have to learn from me anymore. Fantastic. Okay. We'll talk a little bit about ADCs. What did I do? I blasted through these real fast, and I kept you too long. It was horrible. Right. Why don't you take a couple minutes? Talk with each other about what you're confused about with ADCs, and we can generate some conversation about them. Okay? Go ahead. You got any questions?
Not really. Max and there's like the previous ones.
How are they? He thinks he knows.
I looked at the previous data sheets though, and they didn't have like any of the I2C.
Hold on, I have something for you.
Present?
It's the same one that you gave. And I found it in my back when you looked like it.
Like if it's a 3.3 volt thing, it's CM for 5 volts usually into it. It has an upper limit.
Next to what Pacific?
Oh yeah. Oh yeah. All right, what do you think? This group came up with some good ideas after I prompted them. I forced them to think, and they were using their brains for a little while. It was fantastic. But what questions do you have about ADCs and DACs that you're like, oh no, I better learn for this exam? Yeah.
In some of the equations, I see like a 2 to the n versus 2 to the n minus 1.
Yep.
And the minus 1 is supposed to be more accurate. Can
Correct.
you explain why the minus 1 is more accurate?
Because if you just go through the math, that's the actual equation. But all your data sheets are just going to say 2 to the n. Not all of them, but many of them, right? And so it's because if you have like 12 bits, that little thing doesn't really matter. And then there are some intricacies about how you've biased your ladder and that sort of stuff. Yeah.
When it was 3-bit and 2-bit DAC and ADCs, would a question like that be one where you have to use the minus 1 then? Because
Yeah, I don't think we're too litigious on the homework,
okay.
but yeah, that's a small number of bits, so it's going to make a bigger difference.
in the exam, would we need to use the minus 1 since we would know that it's a small number of bits?
I usually don't get, again, I'm not too litigious about this, but if it's like a 12-bit ADC, you can calculate what the delta V is, and it's very, very small, like you're in nanovolts. So, but when I taught it the other way, then students would come in and say, like, this data sheet says it's not like that. And I'd be like, oh. Yeah.
Graph of like a DAC, is it possible to like determine like what the resolution is just from looking at it?
Sure. Like a graph of it, like this the plot. Well, this is not a. This you should be able to figure out. I mean, this just tells you this is 3 bits. But like if you want, like we had an actual image of one. Yeah. You should be able to figure out this one. Now, you might be thinking to yourself, I'm a computer scientist. I got lost. I don't know why I'm here. This is horrible. But you can just go through, see how many switches you have. And then you can, in this particular architecture, you can have more than one switch closed at a time. And now you can figure out this is a 4-bit ADC, or a 4-bit DAC.
I was wondering if you're given like a plot of like a DAC output, like a oscilloscope or something.
Ooh. You have to use some deduction and some reasoning through that one. You could look through and say, well, here's all the steps I can count. So then you could say, I know it's at least this resolution.
SAR
star
Yep.
as far as the conversion resolutions with the number of bits you're using flip. In that case, like your longest runtime would be the number of bits you're using. But like if you made it to your the conversion right away, like you only need flip one bit.
Yep.
Is it no that it or is it just kind of just
So the question is, you have a SAR ADC. Remember, this is a binary search. You're using a DAC to search for the voltage that's closest to this. And what happens if you just got lucky? It happened to be at 50%. You guessed 50% the first time. You're done. What do you think an ADC would do? Somebody on this side of the room, or else all right.
Interrupt early so that because it already has value?
It could do that. You could add logic to do that. But I think the reality is, because the hardware doesn't know, returning an interrupt early actually doesn't solve anything, right? Like, sure, that sample itself can be faster, but later on, like say you're trying to stream serial data through, you're still going to set up a timer on some rate, assuming the worst case scenario, so your sample rate's based on your worst case conversion time. So for your particular microcontrollers, they don't throw off an interrupt faster because of that. There are things that are like parallel ADCs that try to do all the binary searching at once so that you can figure it out faster. Or multiple, they basically have multiple DACs, ADCs together, but typically I just go with the worst case. Does that answer your question? Any other questions about ADCs or DACs? Yeah.
Right? To go into the counter, or like when is the counter being used?
When's the counter being used? The counter is keeping track of the amount of time it takes for one slope to reach the reference voltage, and for the slope to reach the analog voltage.
Oh, and then when the enable's done, the AC value is what's in the counter.
Yep.
Oh, right.
Yep. And so this is nice because now you can change your clock and get higher resolution. Like, wow, that's kind of cool, right? Because microcontrollers are really good at time, and they're bad about everything else. So this is an example where you're using the right measurement form factor that your machine's really good at. Yeah.
Was that a constant current source?
Yes.
A capacitor that makes the voltage go up linearly?
Correct.
Okay.
We could, if we were really excited, derive that together as a class. Nobody wants that. It's just a cool trick of math. Yeah.
So I know it's written as the slope meter using a quote unquote time to measure voltage.
Correct.
And I know you can adjust things like resolution by adjusting sample time with SAR.
Correct.
So adjusting resolution for your voltage. Also, is it using time for getting your voltage, or is it only considered the slope integrator using time?
Well, both of these, this one you could change how fast your clock goes to increase your resolution. You could decrease your clock speed, your clock period, or increase your clock period so that you could converge faster. So you can trade off time for resolution on this version, and you can do the same thing here because you don't have to if you have a 12-bit SAR, you could do only 10 or only 8, knowing that you're going to converge faster. So in both of these, you can trade off time for resolution.
It's I think in a chart, it was comparing the ADCs, and it described which ADC uses time to measure voltage.
Okay.
Is that if it has a timed resolution comparison, that means it's using time?
Well, I would say this uses time to measure voltage because you're actually measuring the time it takes to reach the certain thing.
I guess I definitely agree with the slope. I just wasn't sure if the SAR was included in that because of the whole,
I would say there's a trade-off, but I'm not saying you're probably not using time itself to measure voltage.
So for the slope integrator, you can change the clock so you can control the speed and resolution.
Correct.
Okay. It doesn't. The homework answer says that it can't do that, so I just.
It says it can.
It says it's not programmed.
It's not. Yeah.
You tell those graders. Professor Sample said. Really?
Yeah.
No reason it can't.
Okay.
Oh, this year, those graders are gonna be mad at me. Okay.
The single slope integrator, do you typically have control over both the speed of the ramp and the clock frequency individually, or does one?
Just one.
Just one, okay.
We don't, rarely do you see like slope integrators that are configurable, like as part of an integrated part of like a STM32. It's usually an external module. There's some microcontrollers that have them, but they're really good for like little handheld consumer product devices that are trying to measure something in analog.
So then for this one, am I correct in understanding that you can't actually change sampling time, just the resolution? Because the ramp is gonna take the same amount of time.
Yes. Yeah, that's true. I think this is one of the highest accuracies. So if you want to get like 5.5 digit, or wait, more like an 8.5 digit DMA multimeter, it's going to use one of these. All right, any other ADC questions? Or DAC questions? Yeah.
On the exam, would it just we would need to know that it's a flash ADC versus like when we're doing the problems?
Yeah, that seems pretty reasonable. Yeah, I would probably, that seems fair to me. I think if I looked at these three, I'd say, well, here's this voltage ladder, and if you kind of understand the voltage ladder and that every node you're making a decision, and then you don't really have to know how the priority encoder works or even, what's there. But just seeing this part, you should be able to figure it out. Slope ADC, if you see a capacitor anywhere with a current source going into it and a timer, that's a slope integrator. And then this feedback loop with a DAC and a sample hold circuit and some logic. So I think those are all pretty fair.
Can you explain how the DAC is used in the comparator? Is that to generate the different guesses?
Yes, that's exactly what happens. So usually you start your DAC off at 50%, and then you're just comparing, are you higher or lower, and then you're just jumping back and forth, trying to figure out.
Why do you need a DAC to do that though?
Because it's an analog, this is an analog voltage.
Oh, so it takes that voltage and it.
So it sets is it greater than 50%? VDD over 2, yes or no? And then it does that logic decision. Here, you've set up all your decision points at once, right? So every possible voltage has been generated so that you're making a decision, and you do it very fast. This one is smaller in size, more or less, but it takes a little bit more time because you have to generate each one of these voltages.
So that DAC generates those voltages in
Yep.
the comparator. Okay, got it.
Yep. That's a good question. Yeah.
This slope integrator, I know that the slope is more accurate compared to the every slope increase accuracy, but increases time.
I don't know if there's any triple slope integrators. I haven't looked too far into that. But yeah, you would increase your latency, but you become a little bit more immune to noise and process variation with the dual slope. All right, any other last burning questions I can answer for you before the exam? And it doesn't even have to be ADCs, anything from the review. Okay, yeah.
Sampling rate, that typically is using sort of oscilloscope sample rate theorem where you just do 5 times.
I would say that the most robust way to say is use Shannon's limit or Shannon's theorem for sampling. This is how fast you have to go. Oscilloscope is for you to look at things, for you to be able to look at a signal and understand it without using math to interpret it. So if you're going to sample something in the real world, you should probably go 5 times faster. It's just my rule of thumb for all of you.
Question is use Shannon's.
I'm not going to, let's see. There's a lot of different ways to answer the question, or to ask a question. So most things that are going to be calculation based would probably be Shannon's limit. Because would probably ask you what's the fastest this ADC has to go or something, right, to be able to recover the signal. But if the question was, hey, a human's going to read the output of an ADC, like you, or a user or something, then you're probably going to want to go 5 times faster because it's hard for you to look at a bunch of dots and figure out if that is that what's the frequency that goes through that. You need to have more information. Okay, so we'll talk about DMA. I think there's at least 4 groups that are going to be using DMA today, in their projects. So I wanted to give a quick overview of it, and then next year we'll probably have an entire lab focus on using DMA or using DMA in some way. So I wanted to make sure you all knew what it was in theory, and then you can figure out is that useful for your projects, because it does speed things up and it gives you some complexity points. So the problem that we typically face is, say you have some peripheral out here, say it's an ADC and you're sampling something, and your goal really is to maybe take the average, min, max, that sort of thing that you'll use this, not the actual ADC value itself, but some mathematical average of it is part of your thing. So what could that be? Maybe you're trying to do range, well, that range is not a good one, but I don't know, there's some analog brightness you want to follow the sun or something. You might want to take multiple ADC values so that you know exactly which angle the thing's at. Oh, that's a good one. So maybe you have a servo arm that's sweeping through and you're trying to find some light source. And so now you need a buffer full of some value, and then you imagine you'll find a peak and you got to find the peak of that. So how would you go about doing that? So the naive way to do it is just to do a bunch of load stores. The problem here is you have to go from your peripheral all the way to the core and then load it back over here. So now you have 2 transfers, which is going to take time. And of course, the opposite would also be true when you're taking data out if you're doing DMA or something. Or sorry, if you're doing sound generation and you want to go play a sound over through a DAC, there's actually a nice, I'm sure Matt and James know where it is. I had it at one point, but there's a nice website that will take like an MP3 WAV file and turn it into C code, C binaries, or C array that will just play that sound for you. So that like all that's done for you, which is nice, and you can play actually pretty good sound, like maybe 5-10 seconds. Anyways, you could do that by taking out a memory and processing it through the core. It's just that this blocks your core from doing anything, and it fills up your bus. Not in a bad way necessarily, but it certainly holds down your core. So DMA, direct memory access, is the idea of having some other controller or some other method for directly having peripherals talk to memory or memory talk to memory. It's almost always memory and peripherals talking to each other. And leaving the core available to do some other task. And so that's nice. You imagine if we were going the other way, you'd have your ADC that would just start filling up a buffer as your servo moved the light sensor over the sky, and then after you've gotten maybe 100 samplers or something, then you just tell the core to turn on. That saves a lot of time and effort. So there's 2 general ways to get this done, philosophies. There's what's called, you have a DMA controller, which is on your bus. And this acts essentially like a second core. You don't get to write code for the second core, but you can configure the second core like a peripheral to do a task for you. That task would probably be like, go to this memory address, or maybe on an interrupt, go to this memory address, get some value, and put it into memory at this memory address. And you can set it up to do it circularly, or maybe like a ping pong buffer, or just from one point to another point. And then the 2 modalities are, you can do flow through, which is data will go from the peripheral and be stored in DMA in a register, and then DMA will push it out to memory, or DMA can set it up, basically set up the destination address not being the DMA itself, but being memory. And so now you can pass it through. Now, the benefit of this is that you're pretty tolerant to slow peripherals. So maybe UART would be a good example, where the DMA can go push this through. What you don't want to necessarily have is have a really slow peripheral and a fast memory, and everything's being blocked here. That's where DMA comes through. But if these things have good timing, and tight timing, and they're on the same channel, which we'll talk about later, then you can have the peripheral talking directly to memory, and the DMA controller is just telling things where to go, basically setting up that bus traffic of saying this is the address and that's the destination. And so what that kind of looks like is your DMA controller's here on your high performance bus. matrix, we'll talk about that in a second. And then you could be controlling information going through the advanced peripheral bus and the bridge. Remember, these are generally much slower than the advanced peripheral bus, and the advanced peripheral bus is pipelined. And then this matrix is actually the idea that there are several buses. There's 6 buses for your particular device, and that means that there's a road with 6 basically parallel lanes, and now you can have different amounts of, or different 6 simultaneous destination sources going at once. And so you can imagine, you look here, well, GPIO, ADCs, camera, and USB. These are all pretty high bandwidth things that have lots of data potentially going through them. It's not just one sample. It's repeated things over and over again. Now you can kind of see why the architects chose to put this on the advanced high performance bus, because now you have a direct line to get to SRAM or to flash and to the DMA module itself. So DMA, so in this DMA bus matrix, you have these ideas of channels. You can tell that this was done by engineers and not computer scientists, because it's, starts indexing at 1. But here it just shows you for your particular device what's the mapping. You can see that here all of them can get to memory, but the ADC1 can't necessarily talk to timer 2, so there is some synchronization that you would want to do in planning as you start out your project. If you think you're going to use DMA, you're going to want to make sure that they are on the same channels to have effective transfer. This is for the fly through. You can still get away with it. Sorry, this is the fly by. You can still get it to work with the fly through in most cases, because then you're going to take one channel to the control or to the DMA controller, store that data in there, and the DMA controller is going to send it back out to another location. And you can let's see what else you can see. Yeah, lots of timers. Your SPI. Those are the most of the peripherals that need DMA. And so just as the quick walkthrough, this is the counter example of what you don't want. All right, you don't want to go to the core, so here you can send data directly through the DMA engine, where the DMA engine is controlling the interrupt request. So a lot of this is get an interrupt from UART, okay, that's going to happen. Then it tells UART, okay, send it to SRAM, and then that can all happen autonomously. So there's good tutorials. It takes a little while to set up, but it's not too bad. There's 2 basic modes. We won't go through all the registers, but there's 2 basic modes. There's the incremental mode where you're telling, and there's a couple registers so you can say the direction and the count of how many, do you want to go from memory to your peripheral or whatnot. And it tells you how many times you're going to increment. So there's an increment register that keeps track of it, and then you'll go through and just increment the data. So this is, oops. Slides are kind of messed up. So this is an example of what would be good for like a ping pong buffer. So you can set up 2 of these. You can be filling up one ping pong buffer. Ping pong will go off, set up an interrupt that will tell your core, hey, start pulling data out of this other one. So a lot of these structures are really good for streaming data. That's primarily what they're good for. The alternative one is a circular buffer mode. Oops, come on. I don't know why it looks like that. But the circular buffer mode, basically, it's got a memory address, and it just keeps going. As soon as it gets to the top of the memory address, it keeps coming back down. So circular buffers are another good way to deal with streaming data. You guys learned about circular buffers and ping pong buffers, I assume? Great. Yes?
So in that matrix, I'm confused on the. You were talking about fly through versus fly by, and I was a little bit lost on how to actually not this matrix, the yeah. Is memory supposed to be on here?
Yeah, memory is assumed to be on here. It's to be assumed to be available on a channel.
On every channel?
Yes. But it would be, you can't necessarily talk to SPI receive and send something to timer. Right?
So it's just saying the fly through versus fly by is a fly by doesn't talk to memory and it talks directly to this other peripheral.
Right, you could have 2 peripherals talking directly to each other.
And then the fly through loads it into memory as an auxiliary thing that then allows it to go into another channel.
Yep. Maybe the slight difference from that is flow through actually stores the data temporarily in the DMA module itself before going to memory. And the problem here with this one is it takes 2 memory transfers.
So how does that relate to the diagram?
I think it's just telling you these are the things that can be connected per channel. And what would be, and the real problem here, the real constraint between which one you choose is the speed of your peripheral, right? If it's a very slow peripheral, you don't want to hog that channel the whole time. But if it's an incremental thing like where you would want to release channel 1, let's say, then you just use channel 1 for a moment, have your DMA hold it, and whenever it's available, you can have a blocking thing at channel 1, then it'll talk to memory.
Okay.
That's a good question. So you guys learned about circular buffers and ping pong buffers. So DMAs, thinking about these data structures and why you would use them in a streaming data mode and providing you with mechanisms for this. And so there's a bunch of extra flags you can look through to show you, okay, here I'm halfway through, like you'll get pointers to show you where you are on the circular buffer, and so that your core can wake up and make sure that it's pulling data out from the correct place at the correct time. Yeah, I think these things just got, the labels just got mixed up, but I'll make sure they're updated and put out in the slides. So that's about all I wanted to point out. There's just a couple different modes, and you're going to have to read through the DMA or the bus matrix channels to make sure that you can transfer data at those times. When peripherals are ready to send data, this is where it's all going to be happening in interrupt requests, and DMA is going to be able to take care of that for the core. So the goal was just to give you an overview of DMA so that if you needed it for your final projects, it was available. Are there any other questions? Yeah.
Can you explain what a ping pong buffer is?
Ping pong buffer is just the idea. So say you had some buffer and you're filling it up, right? And your goal is, I want to pull data out of it. I want to fill this up and then pull data out and store and use it on my core. But the problem is, like, if I get to the very bottom, then I'm out of memory, right? So like now the core would have to be very litigious about like making sure where that pointer is and making sure that I'm not running out of memory. So a way to do this instead is you have 2 buffers. They usually call them in code like ping and pong. And so you get an interrupt that says, when I've hit the end of this buffer, then tell the core what to do, and then it automatically switches over to the other buffer. And so now, while this one's filling up, the core knows, okay, I've got to go process all this data, because when I come back to the first one, it's going to overwrite that data. So it's just a data structure that, with a little bit of hardware support, that helps keep track of what the fresh data is. People get really religious about ping pong versus circular. I don't know why.
So if, as far as project, your intention is to, I guess, process information from a peripheral, and at that moment, and not necessarily work out that particular way you process this, and would you necessarily not worry about memory, or like?
I would say, like, if your project is running out, it has real timing constraints. Like you're trying to measure some sensor or UART, you're trying to put a lot of data over UART, or you're trying to put ADCs or DAC, you're trying to play out audio, right? That's a nice time to use DMA, because now your core doesn't have to keep track of that. You could just have a timer that goes off and says, transfer this data over. It could even just be one value, right? Transfer this data, timer goes off at 1/44 kilohertz, and take a value out of memory and send it to DMA. And the core doesn't have to do anything. Right, your core, so one of the problems is you got your DAC that's spinning out sound, and now your core hogs it, or maybe some other interrupt occurs, and your core will corrupt your DMA or your DAC audio output because it's taken too much time, and now you hear like a pause or a skip or a hiss in your audio track. It's because your core has taken up a bunch of, wasn't there for the right timing. Yeah.
I guess this is more of a practical question, but when configuring the DMA controller in STM32Cube IDE, how do you tell it, like, where the circular buffer and ping pong buffers are, because I imagine you'd have to like allocate those in your main.c and then pass in a pointer or
Yep.
something. But you don't know that until after you auto-generate, or does it like allocate the buffers for you?
When you compile it, it'll allocate, you just say this is the variable, right? And then, yeah. So you can look, when you set them up in Cube IDE, you get little variable names and it's hidden, all the details are taken away from you.
Oh,
That compile time. Like you can set them up yourself, like hardcore bare metal C. It's not fun. You'll find, I mean, I'm sure you've already found this. Cube IDE is pretty good at most things that you want to do. But remember, how many people use Cube IDE a year? What do you guys think?
1,000.
100K maybe? Like in the US, like how many people are actually like using a Cube IDE?
20K?
It's not iTunes, right? Like iTunes, they actually make sure it works half the time. I don't know, right? But Cube IDE is like broken, especially at the edge conditions. Like, oh my gosh, you find like, oh, I did some weird clocking tree and like now I have to rewrite it from scratch. Like, so I guess what I'm saying is Cube IDE is pretty good, but just be careful if you're doing really weird things. The WYSIWYG is going to fail you at some point, and just be aware that there are limitations to that piece of software because not very many people use it in reality. It's hard to support this thing. All right, any other questions about DMA? Yeah?
Is it on the exam?
I would think it, so we did talk about DMA earlier in the class, and I just, about all I've ever told you is it's a way to take data from one memory location to another or peripheral to memory without using the controller. That's all I've told you. So if I told you like, go calculate the timing interval for DMA for something, you know, I think that would be outside the scope of the class. I think I answered this on Piazza too. If you had homework assignments on that or a DMA lab, then yeah, I would probably ask you more detailed questions. But now I've already made the exam, but maybe I should go put a DMA multiple choice question on there. All right, any other questions? How many people have made PCBs before? Okay. A quarter of the class? Sometimes we include a PCB lecture. I don't know if it's necessary. Maybe. All right. So I want to talk a little bit about what's expected for the presentation. So these should be about 10 to 12 minutes long. Your job is to create a presentation that ends on time, please. Not too short, please. That will teach the rest of the class how to use these components. The goal was to choose components that are actually relevant for your project, for your team, and then by forcing you to learn them, you'll be more prepared for your own projects, and then you would go and teach the rest of the class, which are probably going to use similar things. So like, I don't know, about half the class projects are going to use XB. So we chose to have, on Monday, we'll have a team talk about XB so that it kind of gives you guys all a primer on how to use that. It also lets us explore a wider number of topics in embedded systems that we wouldn't get to in lecture, okay? And it helps to hit your ABET certification, or our ABET certification of making sure that you present things. So I was going to go through any questions on logistics beforehand? Or what's expected? Yes?
Just go through like the reference manual or like spec sheet. Exactly.
What exactly? I'll go over an example. I took slides from past years for topics that weren't necessarily part of this class. So I'm going to go through them to kind of give you a better example. I don't have like a nice lecture on it, but my guidelines would be in any presentation, understand who your audience is, right? And so you want to introduce a concept, but also like ground it in something that they already know and understand. Because if they already understand it, then they're going to be easy to follow you the rest of the way. But if you just start talking about, I know this one's about RFID, if you just talk about ultra high frequency RFID tags and the integrated circuit inside of it, and like super detailed stuff, they may be lost from the very beginning. They'll have no way to catch up with you. And then the last part is like, think about what the value of the presentation is for your peer, for your group, or for the audience, and that is they might use something here. So they need some tangible, actionable nuggets of information that will actually allow them to achieve a goal. Yes?
This is just like pick a particular component.
Did I?
Like how to use, like you read the data sheet and provide a guide on how to use that component.
That's approximately correct. Now, it would be good if you also gave some background. I don't know, do you know what your thing is?
Yeah. Color light sensing, IR and UV.
Great, so you could just go and say, hey, I picked up the LM5142 and it has a wavelength of this, and that would be kind of like abrupt. People may not understand. But if you said, hey, this is how generally color sensors work. They use photoresistors or photodiodes, and you have to tune, the manufacturers tune the band gap to be able to be sensitive to certain frequencies. And now you're kind of giving some idea of like the limitations of what this technology can do. I'd start off there. And here's the underlying physics principles of how we can do this. And then you're like, and then there's a particular example here we could use, right? And that is this LM52 level. Yeah.
What are your thoughts on using the font Wingdings in our presentation?
Wingdings?
Yes.
What's a wingding in this case? So you gotta be
Font.
Oh, fontant? Oh, Jesus, no.
No? Damn it. Yes.
Well, you can't. Wingdings is unreadable, right?
Yeah.
Like it's not actually like you could just put up gibberish on there. I don't know it'll help anybody. Maybe I can give you general feedback on presentations. If you use Comic Sans, your future boss isn't going to think that you know what the hell's going on. The contents could be good, but it's still Comic Sans. Yeah.
It's more of a teaching thing. Alongside of our presentation, can we use the whiteboard if we want?
If you want to, that's exciting. I don't know why you'd want to. Because usually that means that you have not thought of what you want to present beforehand, right? And now you're on the fly have to explain some idea. So sometimes when I'm interacting with you guys, I'm like, oh, we went off in left field and I better go draw something on the board because I don't have a slide for it. But this should be a well-canned 10 minutes. And it's unlikely the audience will ask you a question that they're not going to ask any questions in the middle of the presentation. So maybe at the very end. I don't know, what were you thinking about doing?
I don't know, if I'm trying to show a shift register, just for example, because we're doing LEDs,
Yeah.
right? I draw the shift boxes, I draw, the things, and I shift them over. I erase, I shift them over, just to show things move.
Could you make a beautiful animation?
I could, but that's so much work.
Oh,
But
I mean,
it makes
yeah,
it makes
doing
more
a great job is work.
But it makes more sense on a whiteboard, I feel. But I don't know, if it's not allowed,
You know
that's
what?
fine, I won't.
So part of this game is that your peers are going to grade you.
Yeah.
So you should come to class. Part of your class participation is coming to class, and you will fill out a form for each team, and then at the end you'll fill out a form to rank the teams and to get some bonus points. And then part of class participation is, did you actually fill out your forms? So if it's, and you'll get feedback on intelligibility and did it make sense. So that's a gamble to play. I encourage you to spend a little bit more time making slides. I know you look at my slides and you're like, man, that guy, he just asked chat this morning to make them. Now, I know you think that. I actually try to make nice slides. It's kind of hard. Any other presentation questions? Go through here. All right. Introduction's fine. Oftentimes I find in presentations that it's a little bit boring to talk about this. Usually want to get through like the motivation or the beginning idea first. But here, what are we going to talk about? I don't know why you write introduction, but RFID frequencies and topics. Okay, so there's a little bit of outline, not a big deal. I don't know if I'd really want to read through each one of these things in a presentation, given you only have 10 minutes. So here, where they're trying to give you a sense of, you've all done this task before of tapping, right? So here, I think they're doing a good job of trying to ground this in something that you know. Right, here is the experience of turning on an RFID tag, use it every day. And then there's three basic elements. So there's an RFID antenna, there's RFID, that's not how I would do it. RFID reader, RFID tag, and then RFID antenna and tag are combined together. And the trick of RFID in general is that it is battery free. There are no batteries inside RFID tag. where do you guys think they get the energy from?
In the device that's tapping.
Yeah, so in the reader itself, right, this thing is beaming power to it. It could be through induction, it could be far field radiation, but it's, you know, a battery-free little device. Okay? And that's the trick. It will last forever, and it should be low cost, right, because you don't actually have to put a battery inside of it. And then they're going to give you some background here. So the idea here is they're trying to tell you that, hey, there's different types of RFID tags based on the physical layer underneath. So there's ultra low frequency ones. This is, I don't know if you have any pets, but this is the pet tracker. They're not tracking, but they put a little capsule injected inside your pet, and it has a little ID, so if the pet ever gets lost, they can be scanned, and now you can get your pet back, right? So it's permanent ID. Those are really low frequency, low range. This frequency here, 13 megahertz, so this is an ISM band. This is an ISM band, this is an ISM band, and this is as well, although it should be 9.5, 950 megahertz. These are the frequencies where it's available for companies to transmit information. All the other frequencies the government has allocated for other purposes, military, scientific, like astronomy things or medical devices. These are about the only places that you could make a consumer electronic devices. There's another one here at 400 megahertz, I guess here, and 6.5 megahertz. You'd actually find that they're all harmonics of each other. So what are they trying to tell you? They're trying to tell you that the range is also proportional to the distance, to the frequency. So a higher in frequency, more or less, the longer distance you can go. It actually starts being a limit about here where it starts to go back down again. And then they're going to show you here some applications. This is the type of coil that would go into your pet, payment systems, and then there's far field scanner. Lots for payment, secure payment, animal identification, and then object tracking. So the UHF stuff will go for, say, 10 meters or so. That's an ideal case. So that's most of this room we could cover with a couple of RFID readers and be able to track coarsely where you all are, but certainly we could figure out who's in the room and that sort of stuff. And I've done some research on that work to try and understand what people are doing in their homes. Then I go through and they talk about the anatomy of an RFID tag. They're going to specifically talking about this module, this type here. This is NFC, and there's a coil of wire here, and there's an IC here, and then the two are bonded. As a side note, RFID tags cost about, I think the cheapest you could possibly buy in volume is about 25 cents or so, maybe 13 cents, depending on how big the IC is. And typically the cost is 1/3 is the cost of the coil, 1/3 is the cost of the chip, and 1/3 is just bonding them together, is the assembly of those things. Now they're trying to say, okay, you have this thing, and how do we turn it into how to take this RF energy or AC energy and turn it into some usable voltage that the piece of chip could do. And they're showing you here's a full wave rectifier. And then a full wave rectifier will just rectify, take the down part of the sinusoidal and turn it over. And what it will do, you put a capacitor on the back end, and now you get something that's approximately a DC voltage that you can use to power a device. It's not a lot of power that's coming through here. This is going to be, in this case, maybe a milliwatt at the very best, but more like 100 microwatts is pretty reasonable for some RFID tags, but it's still usable. And then far field RFID tags. These are about this length. That happens to be half of the wavelength of the wave propagating through space. And there's a tiny little piece of silicon. And this is the one that can be read up to 10 meters or so. What do they want to talk about here? I don't know. Oh, readers and tags. So in this particular case, RFID reader is sending out this magnetic field. So we're back to the coil case, not the far field case. And when you bring a coil of wire in here, so magnetic field here will induce current, and this one, current will drive through, and it'll go through your rectification stage. It'll have some control module, and then to send data back, this is what I think is exciting about RFID, at least the far field version. Oh, I'll talk about near field version first. Near field version first is they short out the antenna, so they don't actually emit any signals. They short out the antenna such that it will load down the coil. More energy will go in here, and then on this side, they look right here. They'll look at how much voltage is going out, and they'll say, oh, the voltage dropped down. Why did the voltage drop down? Well, this thing is sucking a bunch of it, shunting it to ground. Therefore, I look over here. I can tell you that that thing is trying to send me data by looking at about how much voltage I'm actually getting out there. You could think about that as a voltage divider where you're trying to communicate by shorting out the bottom of the voltage divider to figure out if this load is trying to send data or not. The analogy for far field stuff, this is the one we have propagating electromagnetic waves, is that I am an RFID reader and you are RFID tags, but you don't have any power source, so you can't shine any light back at me. I take out a flashlight, I can send AM modulated lights to you, but you can't send it back. So what you do is you take a signal mirror out, just a mirror, and you hold it up and I shine my light continuously and you bounce that light back to me and you modulate it by turning the mirror up and down. Now you can send messages to me. That's exactly how these far field RFID tags work. It's just that instead of sending light, they've gone from like 400 or 40 terahertz, they've gone down to 915 megahertz. Same frequency or same mechanism. They're just bouncing light back, and here we're shorting out the antenna to send data back. So it's great. These things are pretty cool because they can send data, but they don't actually transmit any signals. They only reflect signals. And actually, this is what they were going to talk about here. I got ahead of myself. I talk about how these things they must have talked to me where I told them about the mirror analogy. But look at this graphic. This is horrible. Even worse than my graphics. You guys can do better. Then now they're going to transition to part of the talk where they're trying to make it more concrete for you. I don't know if I particularly would have started this way, but they're going to talk about a particular module that they have in the lab, which is the RCS 522, which is an NFC module. And all of a sudden they start talking about how data is organized in the card. I don't know if that's where I would start. I'd probably start here and say this is what the module looks like. You can see the 0.1 header pins. It's about this big. And this thing has SPI, UART, or I2C interface you get to select. And basically you can talk to it and it will tell you when an RFID tag is here. So now you can have contactless data transfer. The way they were doing it is they were playing, I believe this is the team that was doing Mario Kart, and you would run over something and you would get a speed boost, basically. And by running over it, you'd read the tag, and then you would know, and then and software would increase the available current or duty cycle to that car. There are, just so you know, there are multiple protocols. I think they forgot to say it. This device only does one protocol. It is 14443A. But it's interesting, I think, just because I know this stuff well, that there's another protocol called 15556 that uses exactly the same hardware. Everything's exactly the same, but the protocol allows the chips to be read from further range. You can increase the range of RFID by changing the protocol only. Seems like an amazing trade-off to be had. And then they're going to go through here. They're going to talk about kind of their setup. They have a battery, they have a microcontroller, right, that initializes this thing, talks to the RFID reader. In here you have this antenna, an analog interface, contactless UART, sure, but there's basically a host thing. You're talking to this. There's a buffer that you can send data back and forth, and you can read data back in if you need it. And then a little bit boring demo, right? You've seen RFID, but I like showing demos. I encourage you guys to show demos as well. And here they're just showing these are the sorts of behaviors you can get out of it. I hate terminal demos myself. I accept that we'll see them in this class. But this is pretty boring. It's like, look. Oh my gosh, did you see the text changed? But you can see intuitively this is the range you're able to get out of this particular device in class or from lab. So you all can expect the same sort of behavior and performance if you want to incorporate it in your projects. So I might, for this one, I might have added a little bit more details on SPI and how hard it is to set it up. Maybe they didn't have a chance to actually do that yet. But this is kind of an example of what I would expect from you guys. What do you think? Does this help? Okay.
If you, I guess at the moment, if you didn't have if you want to do a demo, you didn't set your part, you kind of like set up how you would do the demo, but then like maybe take your time. What you're doing is like
So like,
order.
say you were presenting on Monday, and you had some like exam you wanted to study for instead, and you probably didn't have enough time to set up a demo. What could you do? This is essentially your question. So a lot of those things will have, like, one of them's an LCD screen. I bet you can find online an LCD screen, exactly the same LCD screen performing. And now people, if you're talking about what's the performance of a graphics interface, and you just talk about it in the abstract, they never see it, they'll never understand what you're talking about. But showing that demo of somebody else's demo, showing a video clip of somebody else's demo, can help the audience understand. Well, I could, any other questions on this? Yeah. This recording will be. I don't remember what grade they got. I'm sure they did fine. I would not say this is the best possible presentation I've ever seen. I'm just trying to give you an example of what I liked and didn't like about it and what I'm kind of looking for. That's the goal. But this recording will be made available.
I mentioned even like terminal demos. If you were to like make a demo trying to show off RFID, how would you do?
In this class, I wouldn't do terminal demos. For my research, my students, I don't accept terminal demos because it's just boring and nobody understands intuitively what's happening. But for this class, a terminal demo, like, you only have 5 weeks, like, totally acceptable. For your final projects, I hope you can do a little bit better. Does that make sense? Or do you want an example?
I guess in the case it's like the final project we're doing, you know.
I think they're pretty unintuitive because you're like, hey, see, did you see that? That's why I'm so good. Look, that changed. I can't understand anything, but at least you could go. I think let's see if the LED changes when they do things. Nope, doesn't change. At least they could have an LED change, right, that says red, right? And then you're like, oh, okay, I understand the distance. There's something to learn that's more intuitive than trying to look at a screen.
What are you guys and like the peers can be grading us on? Is it just like how good it is? What's it graded on?
I think I have to go look at the metrics, but it's something like clarity, like of presentation. Does it make sense? Did you learn anything? Could you explain the concepts to somebody else if asked? Could you implement it if asked? Now, of course, there's not possible in 10 minutes to make it so you could completely implement RFID, but you should at least not have to start from scratch. So there's some ratings there. If you're real excited, you can post on Piazza, and I'll show what the metrics are. But it's pretty much clarity, depth of content, and can an audience member teach it to somebody else? Yeah.
Will everyone's presentation slides be like available afterwards?
Yes.
Okay.
So you're all gonna, even though I personally do not like Google Slides, because they're horrible, I expect that you all use Google Slides. That's totally fine. If you want to use PowerPoint, don't use Keynote. But we'll have a folder before the lecture that day. It's best if you all put your presentations in the folder, and then we'll have one computer that's queued up. You can just give your talk, and then all the slides will be available for the rest of the class. And then if you just want that quick reference on how to get motor drivers up and running, you can look at that lecture slide. All right, well, I could talk about PCBs. You want PCBs? You don't want PCBs. Or I could let you go. How about raise your hands for let you go? PCBs. Oh my God, all right, let's do it. Yeah.
So for like the final project, if you like run out of ports on the STM32, do you have to use like a PCB then?
If you run out of what?
Ports?
Well, PCB won't help you get more ports, but you could use 2 STM32s.
Oh.
You could use a GPIO expander, which imagine you would use a USB, or sorry, not USB, but like SPI interface to a module that would emulate multiple GPIO pins. So you could get another 32 GPIO pins if you wanted to. The bandwidth will be low and it's not be convenient, but there are these things that exist. In fact, Matt Smith has made you a nice GPIO expander, which is described in detail on the datasheet, which has been released. So you will know all about them. Because he ran out of GPIO pins as well. All right, let's see what horrible slides I have about PCB design. What other question? Any other questions while I get those slides up? Okay. Maybe these slides are a little bit less about how to actually design a PCB. Like the process of choosing where to put your chips and all those sort of things oftentimes is just experiential learning. Like you have to have gone through it a few times. You're like, okay, I'm starting to get this, and you get feedback from people. But if you just start off, I say tomorrow, go make a PCB, and you have no background on like even how they're constructed or what the goal is, then it's super intimidating. So the goal of this lecture is kind of give you the background on how PCBs are made, and so you have all the terminology and generally what the design considerations are. Okay? But not necessarily a tutorial on how to lay out microcontrollers. So PCBs can seem like there's something magical, something like you actually have to know like about electronics and all this sort of stuff, but really PCB is just wires. It's just wires manufactured by somebody else in a particular geometry that's really advantageous to you. So everything that you put on a solderless breadboard is essentially the same exact thing. It's just been made into a purpose-made solderless breadboard, and soldered, this will be soldered, but it's just all the wiring that goes through the components. That's all we're trying to accomplish. There are trade-offs here. Your wires on your wireless breadboard are thick. They can take amps of current. You have to, if you think about high current stuff, you'll actually have to do some calculations on how much current your thing can deliver. But here you can see these little traces in here. So this is, I don't know, some resistor. This is a through-hole resistor. And there's a wire that goes through here, and it goes to some other through-hole resistor. And if you wanted to put an amp through here, you'd have to do some calculations to make sure that's thick, because these traces are only, say, 31 mils, which is 1,000th of an inch. I don't even know what it is anymore. Geez, I've been working in this so long, I only know what mils are. I don't even know what they stand for. But they're very small. And so here's an example. This is a through-hole board, which is becoming more rare here, and where the parts, once you make the PCBs, the parts are placed on here. I don't know where it goes from one to one, but are placed through the board. The more common type is a surface mount, which looks like this. You don't have the hole that goes through. You have a part that sits right on top. And this is nice because on the bottom, this hole goes all the way through, and I can't put things underneath it. So this actually eats up a significant amount of space over time, making layout harder, although it is a much cheaper way to make PCBs. Does anybody know how much a PCB costs to make? Like this big. What do you think? How about $500? How about 2 layers? 2-layer PCB. Who thinks it's more or less than $500? Or how about more? Okay. You want less? Okay. Less than $50. $5. A little bit more? About $5, approximately. So I don't know how big this is, but you can get really cheap PCBs made overseas. Well, with the tariffs now, and we actually got caught by it one time where we had to pay, I think it was like a couple $1,000s for boards because we were making complicated boards, and like 500 of that was tariffs. I'm like, okay, that's fine.
Yesterday.
But you can get them made overseas. Because they're trying to drum up so much business, they usually heavily subsidize the smaller PCBs. So at least a couple years ago, it was not uncommon to pay $5 per board and then pay $50 for shipping. So it's just a penalty of 2 or 3 weeks to get that to get the order shipped here from China. So from your point of view, it's feasible to do it for a class project. I'd want you to talk with me and Matt and James to make sure that it actually fits in your timeline. It's useful to do because we certainly have had teams that try to go for PCB and it fails or something's wrong, and then they come up to their demo and it literally is just a pile of parts and hopes and dreams. And I can only grade things that work. So that was a challenging time to make sure we could give them some points for it because they really didn't have anything to demo. If you're thinking about that, the path is you get something working first and then you try and get enough of your thing working beforehand so that you're like, okay, I know what to build for my PCB. You build that in parallel and then hopefully like in that last week it arrives and you can build it all out. So it's a big high risk, high reward sort of scenario. I don't know what else I want to talk about. If you guys have questions, you can just ask. This is kind of a typical PCB. On it you have, these are called, it's not vias, this is called a pad. So there's this terminology of, I don't know if I agree with everything I put on here. So these are pads. Pads are things that you would put surface mount components onto. You could also call this a pad, even though, well, it is a drill hole, but this is meant for, like especially this one, is a pad is a landing spot, in this case for 0.1 headers, and these would get put in here and soldered on, and this just happens to be a pad with a hole in it. That is different than a drill hole, let's say like this. This is supposed to be a via that only allows signals to go from the top layer to the bottom layer, and so it's plated. It should be like this is a hole with nothing connected to it. This is just for mounting holes for putting a standoff on. This electrically connects the bottom and the top, which means the inside of it's plated. The same thing happens here. There's no real, from the manufacturer's point of view, there's no real difference between a via and a pad with a hole in it for through hole, but your CAD software makes a big difference about it because they have different usages. So pads, hole, let's see, mounting hole, via, and a hole in the pad. And then this is also, this is a surface mount, dual inline package, something, that is, you would put your chip on here and solder it up. The green PCB is, usually PCB is like a tan color, and then they'll go and they'll put material color over it. And this is the silk screen, or no, this is the solder mask. And what it's doing here is you have a pad, and this is tin copper. So tin is a material that keeps the copper from oxidizing. And then you can see this trace here is actually greenish. That's because they put the solder mask over everything except for that pad. And so this protects solder. So one way that they make PCBs is kind of amazing. If you go back to here, like this PCB, they take the whole thing, they put all the parts in here, and then they have, it's called wave solder, and they have a tank of liquid solder, and it's actually flowing over a little waterfall, and they take the PCB with all the parts on it, and they just run it through. And my brain says, that's a disaster. If I did that, I'd have solder everywhere, and it would be a big mess. But if you do it properly, that's the way you can solder everything from the bottom in one pass. And so that's why these are so cheap. You don't even have to put them in an oven. You literally, now they have these little tracks and just kind of go just like that, and the whole thing will be immersed on the bottom and get soldered in one go. So that's why these are cheaper electronics typically than surface mount like these, because these, you have to place everything down, you have to put the solder paste here first. Solder paste is just small particles of solder in a suspension, and it makes this little paste. You would put it down on a pad using a solder a screen, like a silk screening process. And then you put your parts down on it, and then you put that whole thing in an oven. That's just much more time consuming than this task. That's one of the reasons those things cost more. This is an example of, what is this, a 5-6 layer board? This would be a sliced representation. And so typically, we think about the top layer and the bottom layer. When I started my PhD, 2-layer boards were cheap, and 4 layers was like, oh my gosh, how, like impossible. Like this is too expensive. Now 4 layers is just the same as 2 layers almost. If you get 6 or 8 layers, it's still pretty affordable. There just has to be a good reason why you need extra layers. So the green here is the solder mask that is chosen to be over the copper if you want it, or you can leave it exposed. Then they have, what's this? It has some what's this? I'm using different terms than I would use. They have pre-peg, and a core. So here's the core material, and then pre-preg. Basically, they're going to take 4 pieces of FR4. So the copper. So FR4 comes with, FR4 is an epoxy. That's FR4 stands for Fire Retardant Class 4, which means that it's unlikely your PCBs are going to burn a lot. You can burn them a little bit easily, but they will not burn on their own. So you have to use what's called FR4. If you ever need to cut FR4, it's fiberglass, it's toxic, it gets in your lungs, it'll cause cancer eventually, so don't do it a lot. Not immediate cancer, it's just eventual cancer. So let's see. This right here is this is the core. So the core comes with copper on top, copper on the bottom, and then they etch away all the stuff. We'll talk about that later. And then they put pre-peg in between, and then they make a big sandwich out of it, and then heat the whole thing up. And so here you can see that each layer you can put copper on it to begin, or coppers on it to begin with, and then they etch away all the places where they don't want copper. Then they'll come through and drill holes through everything. And now the problem is that as you align, all these boards have to come together, and all these vias have to be aligned up. And this is actually a tricky process. And so what the manufacturer will tell you is, for a particular drill size, they want what's called an annular ring. You can kind of see part of that ring here. They have to have a size that's big enough. So imagine they're trying to hit like a dartboard. So you can see this is an example of when you're going to draw stuff. I was not prepared. I went off on a tangent. Okay, so you have a ring, and this is going to be your hole. So this is the thing that's drilled, but this is all copper as well. And they're saying, I need to have enough copper here so that if I'm off, say I'm trying to do alignment, and my next hole is over here, is off by a little bit, I can guarantee all these things will align. It's giving them a little buffer room so that they can be misaligned. So that's why these annular rings can be pretty large. Does that make sense? Okay. I teach all my students, typically we start with a 4-layer board. So components on top and bottom. 1 layer, it doesn't matter which one it is, it should be a ground plane. You should pour copper. You don't pour copper. You tell your tool, pour copper. Ultimat still calls it pouring copper. And that will just be a ground plane that goes through everything. You don't necessarily need a power plane for most designs. Power planes are fine if you got a 14, 20 layer PCB. You don't really need it. You can just have wires themselves going through the power plane or that other inner layer that goes throughout you need, and then you can use the other space for routing signals as well. That's my suggestion. Any questions so far? Randomly just talking about PCBs by myself. All right. Go a little bit through the manufacturing process just so you kind of know why your design tools keeps asking you these crazy things, and like why they're really worried about silk screen and silk screen keepouts and all this other stuff. So this is our goal. We're trying to get to something that looks like this. Actually, this is your first goal is you're going to make Gerber files. So after you've gone through and you laid out your copper in CAD, I should have a nice image of that somewhere, but imagine in CAD you've told it, I want all my copper here, I want my traces here, and then you got some things on the bottom I want. Those are going to make file types called Gerbers. Why? I don't know. I don't know why they're called Gerbers. I wasn't around then. But they're basically a slice of each layer of, it only says where I want copper. There's OBD2 files as well that tells you how those copper things are connected, but for what you're going to do is just Gerber files, and basically it's just a, no copper versus some copper. That's it. And that's the file you send, and you send one Gerber file for each layer in your PCB, and that could be all your metal layers, but also your silk screen and your solder masks and your all those layers. So you start with a FR4, copper on both sides. Okay. Then they're going to go through and they're going to drill holes through everything on here, right? So they're going to drill holes. Let's see, what are they going to do? And then they're going to electrolysis plate? I don't know. They're going to plate the copper. They're going to try and plate. Yeah, they're going to try and plate the holes. They're trying to connect the holes in here from the top to the bottom where they're supposed to. So that's a challenge in the sense that FR4 is not conductive. And now you need a mechanism to actually, it's an interesting chemistry problem of how do you get copper to stick to something non-conductive. Well, there's a bunch of interesting chemistry that I was not willing to reproduce in my lab. So that's when I learned about it. Next is you need, so here you have copper-filled holes, but now I don't have my design yet. So I need to get my design on this, and I'm going to remove the negative of my design. And so what they do is they apply photoresist to it, where they're going to, it's either photopositive or photonegative. I don't know, it depends on which one you're going to use, but a photoresist, they're going to put it on here only, and then they're going to use light a light pattern through a mask to make certain regions hard or soft. And basically what you do is you go through and I think in this particular one they're using positive. So all these little areas right here, they're going to keep the photoresist on. So they're going to shine light where they want to keep copper. And then they use an acid and they eat away all the copper where there isn't photoresist. So now you can use light patterning mechanism to define where your copper is going to be. And then you remove everything that where the photoresist was not, and then you go and plate the copper with tin. And the reuse tin is that it's non-reactive. Oh, I think I got out of order here for this particular PCB masking process, but I guess now they've gone through, after they've tinned, they're going to go and dump it in acid, and they've eaten away everywhere else. That, remember, it started with copper, and now they've eaten away the copper, so it's a lost process in that sense. And then after that, they're going to go and put PCB solder mask on. So remember here, I probably can't see anything because the image quality is bad, but there's traces here and there's pads here, so both are exposed. By putting solder mask on, you ensure that no solder can attach here. And this comes back to the idea of if you're taking that thing and using wave solder, if solder is going everywhere, you want to protect it so it's not going to jump a bridge across here. This is not going to be covered with copper. With solder. It's not just generally good to have extra stuff around, and it can cause more errors. And so that's why the solder mask is there, just to protect those traces. Okay. Then you get a silk screen layer. Silk screen layer is for you. You're trying to help yourself in the future when you're trying to assemble it. So I've certainly seen some 373 students say, oh, I just didn't get to silk screen. And then they're like, they get boards back and there's no numbers anywhere, and where do you put R2? Like, oh my gosh. It's an amazing decision to have that happen. But you get to go and put silk screen on there, and so take a little time. You take, it's just you and some good music and CAD pushing polygons around, and you're hoping, put silk screen next to your component. There's some standards you can use, basically trying to align them all in the same direction, make it easy for yourself. Now it's cheap, you can get silk screen on top and bottom. There was a time when that was actually an extra cost. And then what's this finishing thing? Maybe they're going to refinish it with tin again. I'm not exactly sure. There's different ways to get your PCBs to arrive to you. What they're going to do is they're not going to make an individual PCB. Typically, they're going to panelize it. So their equipment set up to say, take PCBs probably about this big, 2 feet maybe by 1.5 feet. And the big manufacturers, like PCBWay and JLC PCB, they have a set of requirements. They say you can have PCBs that are this size, and they have to have this trace tolerances. That's because they're saying I expect to be making 40 different PCB projects today, and I want them to, as many of them, to go on the same piece of material as possible. So they'll batch your design with everybody else's design, and then send it through their process, and it'll come out something like this. So this is like panel routing, and then what they'll do is they'll break it off and package it up for you. You can get things that you could ask them, or you could make your own panels. I certainly did this when I was at Intel. We were making really small things because the boards were so small that our assemblers, these are people that will put the parts on and solder them, could not hold our boards. They were just too small to hold. So if we just handed them our boards, they'd be like, well, it's cool you spent $6,000 on them, but I can't, this is too small. So what we knew is that, obviously it wasn't this board, is that we gave them panelized boards. Now their equipment could hold onto it easier. They would put the parts on there, bake everything at once, and then break the boards apart for us. So this is an example of something that was panelized. They didn't do it for size, they probably just did it for cost. And then they're fully assembled, and then you break them off and you can use them. We talked a little bit about vias, that's fine. We'll talk about clearance and I'll let you guys go. So clearance, there's probably 3 numbers you need to know for any PCB manufacturer at kind of like the hobby graduate level, even if it's a small startup. And that is, what is the minimum trace size that this process will allow? 6 mils is kind of a non-aggressive but good size. And they're saying, my traces, their fabrication techniques will not guarantee the traces less than 6 mils will be manufactured correctly. Doesn't mean your entire design should be 6 mils. That might be risking things. And certainly signal integrity and power consumption reasons you might want to definitely have larger traces, but they're saying 6 mils is the smallest we can make. The next one is clearance, from one trace to another one. What's the minimum clearance they can have? And typically, for JLC PCB, and PCBways, that's like 6 mils as well. So it would be 6 and 6. But sometimes you might get down to 4, depends on what you're looking for. It depends what you're willing to pay. And the last one is minimum hole size. So that might be 6, 6, and 8, where 8 mils is the smallest drill size that they'll allow on that PCB manufacturer. So those 3 numbers you have to keep track of. Trace thickness, clearance, and via size, what's the minimums. But whenever you guys make a PCB, the first thing you do, you figure out which vendor you're going to, and then you import their design file, or their design rules into your CAD software. So I have definitely personally made the mistake of designing a board that could not be manufactured because I didn't put the design rules in. Now, thankfully, I wasn't that far off, but I had to go and redo some of my design and move things out because the manufacturer we ended up going with couldn't support my design files. All right, so hopefully that's a little bit of a primer on PCBs. I'll let you guys go. And I'll see you on Friday.